We talked before about one way of solving the approximate matching problem using the pigeonhole principle. And in this lecture, we're going to discuss a new family of methods that use dynamic programming and the idea of edit distance. But they also solve the approximate matching problem. This new family of methods is very, very flexible. It's used to solve many different biosequence analysis problems, including global alignment and local alignment, which we'll also talk about soon. Dynamic programming and edit distance don't depend on any exact matching algorithms in the same way that the pigeonhole principle method did. So we'll think of it as being a separate class of algorithm from the kinds that we've examined so far, which is why I'm showing it here sort of off on the bottom by itself. So we've seen two different ways of measuring the distance between a pair of strings, Hamming distance and edit distance. And Hamming distance is the distance between two strings that are of equal length, and it just equals the number of substitutions that are required to turn one of the strings into the other. Edit distance is defined as the minimum number of substitutions or insertions or deletions required to turn one string into another. So here's a question. If I give you two strings that are of the same length and I ask you to find the Hamming distance between those two strings, is that easy or is that hard? Well, it's actually quite easy. So basically the way you would do it is you line up your strings, x and y, and go through position by position, comparing each position. And in every case where you find the corresponding characters mismatch, you would add 1 to a counter. And then at the end of the day, you would just report back that counter. So that's pretty easy. So how about an algorithm to calculate the edit distance between two strings? Is that easy? Well, that's actually harder. It's really not at all obvious off the bat what this algorithm could be. But before we discuss what that algorithm is, here are a couple of warm-up questions to get us thinking about Hamming distance and edit distance. So let's say that we have two same length strings, x and y, and we'd like to say something about the relationship between the Hamming distance of those two strings and the edit distance of those two strings. Are they equal, or is one of them greater than the other, or greater than or equal to the other? What can we say about these? Well, one thing we can say is that the edit distance between x and y will always be less than or equal to the Hamming distance between x and y. In other words, if you allow me to use only substitutions to turn x into y, I can do this with a certain number of changes, certain minimal number of changes. If you additionally allow me to use insertions and deletions, I can potentially do it with fewer changes. So here's an example. So here are two same length strings, x and y. And what's the Hamming distance between x and y? Again, that's not too hard. We can just sort of go across and count the mismatches. So 1, 2, 3, 4, 5, etc. It actually adds up to 10. So the Hamming distance between x and y is 10. And now what's the edit distance between x and y? It turns out that it's 2. So because these two sort of strategically placed insertions and deletions are all that's needed to turn one of the strings into the other. So the ability to use insertions and deletions in addition to substitutions is something that allows us to potentially get from x to y with fewer changes. Okay, here's another question. So say that x and y are different lengths. What can we say about the edit distance between x and y in terms of their lengths? So can we, for example, put a lower bound on the edit distance between x and y? So yes, the lower bound is that the edit distance has to be at least as great as the absolute difference between the lengths of x and y. Why is that? Well, because in order to edit x into y, let's say, for example, x has length 2 and y has length 4. In order to edit x into y, we at least have to introduce as many edits as is required to make them the same length. We might then require some more edits to make them exactly the same sequence, but at the very least we have to make them the same length. So the number of edits, the edit distance between two different length strings is at least equal to the absolute difference in their lengths. Okay, so on to an algorithm for finding edit distance between two strings. So the idea behind this algorithm, the basic idea, is that if we have two strings and we would like to know the edit distance between them, it helps us a lot if we know the edit distances between prefixes of those two strings. So for example, here I have two long strings, x and y. Imagine they're very long, which is why they're shown sort of disappearing off to the left here. And then we have to imagine that they're very, very long and that we're only really looking at the ends of the strings. That's why they're kind of fading off over here. We're only looking at the very end. And say we know the edit distance between the prefixes of the two strings that are highlighted here in red. And let's say the edit distance between those two prefixes is 147. Okay, so this means that the minimal number of edits required to get from one of those red strings to the other red string is 147. And so to get from x to y, to get from the complete string x to the complete string y, one way we can do that is to first edit the red prefix into the other red prefix, first make those 147 changes that are required to turn one red prefix into the other, then make one more change, then make one more substitution, which is to turn this C into this A. So one way we can turn x into y is to first turn this prefix into this prefix, and then do one more substitution. So that would require a total of 148 edits. That's the kind of principle that we're going to apply. If we know the edit distance between prefixes of the two strings, we can calculate the edit distance between the entire strings. So let's write these two strings x and y in a slightly different way. We'll just replace the big long prefix, the red prefix that you see here, with the Greek symbol alpha in the case of the string x, and with the Greek symbol beta in the case of the string y. And now we can write the strings as alpha followed by c, the base c, and beta followed by the base a. So the edit distance between these two strings can be calculated as the minimum of three things, three terms. Let's look at each of these terms. So the first term here equals the edit distance between alpha and beta plus 1. And so what this term is saying, which is basically what we said before, is that one way that we can edit the first string into the second string is that we can first edit alpha into beta, then do one more substitution in order to turn C into A. This second term here says that another way we can edit the first string into the second is by editing alpha C, alpha followed by C, by editing that into beta, and then inserting an A on the end of the second string. So to say that again, we can edit alpha C into beta, then insert this A. That's another way we can turn one string into the other. And then the third term says that another way we can do this is we can edit alpha into beta A, and then insert a C at the end in order to make the strings the same. So one or more of these three different ways of editing the first string into the second will have the minimal number of edits. So if we take a minimum of these three terms, that gives us the answer that we're looking for. Okay, and we can generalize this expression so that it's not in terms of these specific strings and these specific bases C and A that you see here. So let's just modify our expression here. So now we have alpha followed by x, which is a variable that could be any base, and we have beta followed by y, which again is a variable that could be any base. And we can rewrite our expression this way, and it's very close to what we saw before. But one difference is this delta function here. There's this little expression here, delta of x comma y. What does that mean? Well, delta is just a function that returns 0 if x and y are the same, or it returns 1 if x and y are different. So this makes sense because, again, the interpretation of this first term is that one way we can change the first string into the second is to change alpha into beta, and then possibly, if needed, to add one more substitution to turn the final character of one string into the final character of the other. But sometimes those characters will match, in which case we don't have to add one more substitution. So if the delta function is 0, then they match, and we don't have to do an additional substitution. If the delta function is 1, then they don't match, so we do need to do an additional substitution. So that's what that delta function means. And so at the end of the day, we have this expression. And this expression could be considered like a recursive function. It's like a function that calls itself. That is, if you want to find the edit distance between two strings, you first could find the edit distance between pairs of strings, one of which might be a prefix, one or both of which might be a prefix of the two strings. And to do that, this function can call itself recursively. So to make that clearer, let's look at some actual Python code. So here is a snippet of code that you could use to solve the edit distance problem. This very first line of the code is evaluating the delta function. So it simply evaluates to 1 if we have to add a substitution to turn the final character of one string into the final character of the other. This expression here is a minimum over 3 terms, which correspond exactly to these 3 terms here that we just discussed. So in each term, we're recursively calling a function called edDistRecursive, this function here. So now let's write all this code in the form of a function called edDistRecursive. Here it is. Here's the code we just saw, except it's part of this function, edDistRecursive, that takes 2 arguments a and b. And this function isn't quite what we want. The problem with this function is that it doesn't know when it's done. Right? So in other words, this function will keep calling itself with shorter and shorter prefixes as arguments until eventually we'll get to the point where one or both of the arguments is actually the empty string, at which case we know what the answer is. The edit distance between an empty string and some other string is just the length of that other string. So at that point, we don't have to make any more recursive calls, but as we've written it, the function isn't smart enough to know that. So in addition to what we've already written, we want to add a little bit more. We just need the following checks, so that now we check if either or both of the strings has length 0, then we'll simply return the length of the other string. Now we know when we're done. So now we have a function that works. This is a function that will return the edit distance between strings a and b, though it has a problem, which we'll see in the following lecture.